Hi, everyone. My name is Bibhushan Shakya. I am an associate research scientist at Johns Hopkins University. So the theme of this meeting is priority violation, and one of the main reasons priority violation is important in our universe is because it likely plays a role in the creation of the baryon asymmetry that we see in the universe today. So today I'd like to tell you about an idea for producing this asymmetry through what is known as a cosmic collider. And I should give you the distinction that a cosmic collider has nothing to do with the cosmological collider physics program. So these are completely independent and unrelated ideas. So I'll tell you about a cosmic collider today. So before I start my talk, I would just like to list all of the references that are going to form parts of this talk. And so if you're interested in any particular direction, you can just go ahead and look at the relevant paper. Of course, I won't be able to cover all of these details today. I'll just be able to give you sort of an overview. The main one that is related to this talk will be this paper called Leptogenesis via Bubble Collisions that was written with Martina Cataldi, who's a PhD student at Daisy. Okay, so the physics that we're interested in is a very familiar one, a very well-known one. It's the idea of leptogenesis. Leptogenesis makes use of this idea that in the standard model, the neutrinos are massless, but in reality, we know that neutrinos are massive. And so there needs to be some new physics that is responsible for creating these neutrino masses. The simplest of these ideas is the type 1 seesaw that posits that there are right-handed neutrinos that are standard model gauge singlets that are part of nature, and they couple to the standard model neutrinos through this Dirac mass term that you see in the Lagrangian, the first term. So they couple to the Higgs and the standard model neutrinos. And they also have a Majorana mass. And because this mass is not protected, most likely it is at some very high scale. So for example, if you want to explain the right neutrino masses, then if this coupling in the Dirac mass is order 1, then the right-handed neutrino mass is about 10 to the 14 GeV. And leptogenesis is this idea that if these right-handed neutrinos exist in the universe, if they were produced at some early point in the universe when the temperature of the universe was very high, then their decays would naturally produce a lepton asymmetry that through spin-around processes could be converted into a baryon asymmetry. And this is a very nice and straightforward way to produce the lepton asymmetry and then the baryon asymmetry that we eventually see in the universe today. And this works really nicely out of the box. And that's why this is one of the most elegant ways to explain the baryon asymmetry of the universe. So this mechanism is very nice, but it has, let's say, some problems. Problems in quotation marks, because these are not really problems per se, but just some aspects that are undesirable and could be maybe improved. So there are three in particular that I'd like to address. One is that this mechanism has no experimental signals. So if this is the way that the baryon asymmetry was produced in the universe, then there's probably no way to experimentally test it, especially if the right-handed neutrinos are at some very high energy scale. The second point is that this also requires very, very high reheating temperatures, right? So if the right-handed neutrinos are at 10 to the 14 GeV, then the universe needs to have been reheated at temperatures that are greater than 10 to the 14 GeV. Otherwise, these right-handed neutrinos would not be produced in the early universe, and we would not be able to create a lepton asymmetry that way. The third point is that in this high mass regime, there's known to be very strong washout effects, which means that there are also processes in the thermal plasma that wash out any asymmetry that the decays of these right-handed neutrinos would produce. And so to make sure that the asymmetry that is produced survives to the level that is needed to explain what we see today, needs very extensive and careful calculations. So these are all aspects that are somewhat problematic in the standard leptogenesis scenario. So the new idea that I'm going to talk about in this work is to produce the right-handed neutrinos through a non-thermal mechanism, not out of the plasma, but through a different mechanism, which is going to be collisions of very high energy bubbles during a first order phase transition. And so this simple modification already addresses all of these undesirable aspects of leptogenesis that I mentioned earlier. For example, now when you have a first order phase transition, you most likely have a gravitational wave signal. And so this gives you an experimental signal that we can go out and look for as a companion to this leptogenesis idea. The second is that it does not require very large temperatures, because the idea is to pump a lot of energy into these bubbles when they collide. And so you can have a phase transition at a very low energy scale or low temperature. And these bubbles would still have enough energy to produce right-handed neutrinos that are much, much, much heavier than the temperature of the ambient plasma. And so you don't actually need to reheat the universe, sorry, to a very high reheat temperature. And the third point is that because the temperature of the plasma is so much lower than the mass of the right-handed neutrinos in this setup, there is by construction no washout effect because the plasma is at a much lower temperature. And so whatever asymmetry you would produce out of the right-handed neutrinos that are produced to these bubble collisions will automatically survive in the universe. So these are all now very desirable aspects of this modified leptogenesis setup. Okay, so the physics we're interested in is a first order phase transition, like I said, right? And this is involving the transition of a scalar field in the early universe from some metastable vacuum to some more stable vacuum through some tunneling event. And in physical space, this is realized through the nucleation of these bubbles of the stable vacuum in a background of the metastable vacuum that just grow and convert all of the space into this new phase. And in this process, all of this vacuum energy is released into the universe. And so the crucial thing to look at here really is how does this energy transform as the phase transition proceeds. So this energy can really only go to the surface of the bubble. There's nowhere for it to go, right? And once it goes to the surface of the bubble, if there are efficient interactions with the surrounding plasma, then that energy could be transferred into the plasma. But if there's no way to convert them efficiently into the surrounding plasma, then the energy stays on the bubble walls. And so as these bubbles grow, the energy will just collect on the surface of the bubbles, and the bubble walls will just get more and more and more energetic. And so you can imagine that by the time these bubbles find other bubbles and the bubble walls collide, you've created a very, very high energy collision process. In other words, you've created a cosmic collider. So this is what I mean by a cosmic collider. These are very high energy collisions of vacuum bubbles. So we can estimate how much energy there is in a bubble collision process. So purely from energy conservation arguments, you can convince yourself that the energy density on the surface of a bubble will grow linearly with the size of the bubble. And that's because the energy is getting released from the volume of the bubble, right? The vacuum energy, and it's getting collected on the surface of the bubble. So the volume goes as R cubed, the surface goes as R squared. And so by energy conservation, the energy density must grow as R, as the size of the bubble. And so if you just plug in different quantities and do these estimates, it turns out that the energy density on a bubble wall surface per unit area is roughly of order the Planck scale. And so if there's one bubble in a Hubble volume on average, then the energy is roughly m Planck. If there's more than one bubble, and that's parameterized by this quantity beta over h, then the energy density goes down accordingly. So it goes down as m Planck divided by beta over h. And intuitively, the physical scale that is at play is the time scale over which these bubble walls will interact with each other, right? And so when these bubble walls get energy, they get boosted in the plasma of the in the rest frame of the plasma, and so the the length of the bubble is Lorentz contracted. And so if you estimate what the Lorentz contracted length of the bubble wall is by the time these walls collide, that is roughly of order m Planck, and therefore the time scale for these walls to cross over each other, because they're traveling at essentially the speed of light, is also m Planck. And that is why the collision is really sensitive to this really high energy, despite everything starting at sort of energy scales of the temperature or the vacuum energy, or the VEV of the background field. So to calculate how much energy you can convert into particles, or how many particles of very high energy or mass you can produce from these bubble collisions, what you have to do is do a calculation that involves the effective action formalism. So what you need to calculate is the imaginary part of the effective action of the background field across this collision process. So the real part tells you how the bubble configuration evolves. The imaginary part tells you how much of the energy has gone away into other states. So in other words, how much of the energy has been converted into particles, right? And if you do this calculation, what it essentially does is that it decomposes the background field excitation into definite Fourier modes of definite energies. And so you can think of the collision process, which is a classical process, as a collection of excitations of the background field with definite energy scales or definite momenta. And each excitation that is off shell can now decay into particles that couples to the background field with some probability. So if you integrate over all of these excitations and all of these decay probabilities, you'll get the number density of particles that you produce per collision per unit area of the bubble walls colliding. And so this is the way to do the calculation. And so there are many aspects of this calculation that I've worked on in the past few years. So these are, let's say, the crucial takeaway points of these papers. So the main takeaway point is that the energy distribution of these excitations is roughly something that falls with the power law, which means that some very, very high energy excitation that is much higher than the temperature of the plasma would be suppressed by the fourth power of energy. So it falls as 1 over e to the fourth, which means that higher excitations are suppressed, but they're only suppressed by a power law, so they can still be sizable. And it turns out that this is a fairly universal behavior that is applicable to essentially all kinds of ultra-relativistic collisions. And this is now supported both by analytic arguments as well as by numerical simulations. So you can look at these papers to understand this better. There are also subtleties regarding the calculation. In particular, in some cases, these calculations turn out to be gauge dependent, but there are ways to make sense of these calculations. So you can look at this other paper to understand these things. But let's get to leptogenesis, right? And so now the idea is that you have a background field that undergoes a phase transition, and in that process, it creates bubbles that are moving at very ultra-relativistic speeds. And so the other ingredient that we need is you need to couple the background field to the right-handed neutrinos. And here I can do it through this Dirac mass type coupling. So it's basically mimicking what you would get in the standard model to create a coupling between the right-handed neutrinos and this scalar field and some other fermion in the dark sector. And now the idea will be that when these bubbles collide, bubbles of this background field phi, you get these off-shell excitations in the collision process, I call phi star. And these excitations through this Dirac mass term can decay into this fermion combination and produce right-handed neutrinos. And once you produce these right-handed neutrinos, and remember that these can have masses much, much, much bigger than the temperature of the ambient plasma, then these right-handed neutrinos will just decay and produce a lepton asymmetry. And as long as the temperature is above this, the sort of the electroweak scale so that the sphalerons are active, you can convert that lepton asymmetry into a baryon asymmetry. And so that part of the calculation is just standard leptogenesis. So this is just one example, right? Using what I call a neutrino portal. There are other kinds of interactions between the background field and the sector containing the right-handed neutrino that will also get the job done. So you can again look at the details in this paper. But for now, I'll just focus on this one mechanism. And let's just look at the parameter space where leptogenesis works. So on the x-axis, I'm showing you the VEV of the background field. And on the y-axis is the mass of the right-handed neutrino. And essentially what this is telling you is that there's part of parameter space, which is in white, where leptogenesis works, essentially. So in the brown region, you don't create enough of a baryon asymmetry because you don't produce the desired number density of right-handed neutrinos. But in the white region, everything works. In these other colored regions, there are various other processes that become important, but it still works out in the end. But the takeaway message here is that for very, very high mass right-handed neutrinos, right, let's say 10 to the 14 GeV, you can have a phase transition that is at a much lower temperature. So here it's about 10 to the 12, 10 to the 13, 10 to the 10 GeV, even 10 to the 9, and it's ending up creating the right amount of asymmetry. So as I told you, there's also a companion signal in gravitational waves, right? And it turns out that you need phase transitions that are at least at about 10 to the 9 GeV or higher. And that's just because you need to create a minimum number of bubbles in a unit volume to create the right amount of asymmetry. Otherwise, you would just not produce enough number density of right-handed neutrinos. And so that forces you to have high scale phase transitions, but they're still within range of upcoming experiments like the Einstein telescope or the Cosmic Explorer. But unfortunately, you won't see them with things like LISA or the PTAs. Just a side comment that this is a constraint that only exists for leptogenesis, right? So for other BSM applications like dark matter production, this phase transitions at even much lower scales would work very nicely. So this is only a quirk of the leptogenesis scenario I'm presenting to you today. Anyways, for these future experiments, you would be able to see these gravitational wave signals. I just want to make this side comment that the gravitational wave signal that I've shown you earlier is coming through the standard source produced by bubble collisions. But there is a secondary production mechanism for gravitational waves that becomes possible in these kinds of setups, which is that when you collide these bubbles and produce very, very high energy particles, they have this non-trivial distribution that is dynamic, right? And so if they were to survive for an appreciable amount of time, then this would create an additional source of gravitational waves in addition to these bubble surfaces. And this is something that is relatively new and has only been pointed out last year. So this was this paper that I wrote with these people at Hopkins. And so this would produce a secondary source of gravitational waves, and that would look like this. So the sound waves and the bubble walls are the standard sources of gravitational waves. But if you have these high energy particles coming from the bubble collision process, those could also produce this secondary component that is shown by this blue curve, and that would modify the gravitational wave signal that we would see at these experiments. So this is also something to keep in mind. Okay, so it seems like there's a nice story here which requires a phase transition in some scalar field that couples to the right-handed neutrinos, right? And so the obvious question you might ask at this point is, does this work with the electroweak phase transition? Because we already know one scalar field that exists in nature, that is the standard model Higgs. And we know that it couples to right-handed neutrinos if something like a type 1 seesaw is realized to explain the neutrino masses. And so you might ask, if there's an electroweak phase transition, then does this mechanism also produce leptogenesis, also do leptogenesis at low energy scales? Because that would be quite nice and quite minimal. Unfortunately, the answer to that is no, and it's no for two main reasons. One is that the electroweak phase transition would occur at weak scale, so let's say a temperatures of order 100 GeV, and this is already pretty low in energy in temperature, because remember I told you, right, that you need a phase transition scale at least of a 10 to the 9 GeV. Otherwise, you just don't have enough number of bubbles or colliding bubble surfaces to produce the desired amount of asymmetry. And that turns out to be the case for electroweak phase transitions, if you want to produce right-handed neutrinos and do leptogenesis this way. And the second reason is that these Higgs bubbles in electroweak phase transitions actually don't travel that fast. They don't reach ultra-relativistic speeds, and that's because they're very tightly coupled to the standard model plasma surrounding them. And so as they expand, they quickly transfer most of the energy to the surrounding plasma, and they actually don't move at relativistic speeds. So you would not be able to do this anyways with these electroweak phase transition type setups. But that's not the end of the story, right? Because the Higgs is richer. In particular, we know that there is probably a deeper, higher energy minimum at very large field values. This is what the current standard model measurements seem to tell us, that the Higgs actually becomes unstable at about 10 to the 11 GeV. And if you go to higher field values, then the Higgs develops a deeper minimum that is actually the global minimum of the Higgs potential. And so if you think back to the beginning of the universe, then it's quite natural that the Higgs actually began in this deeper minimum, and then the dynamics of the reheating of the universe transferred the Higgs from this deeper minimum to the electroweak minimum that we see today. And actually, it turns out that the dynamics of this process is such that there is a first order phase transition. So when this true minimum gets lifted by thermal corrections as the universe reheats, then it becomes possible for the Higgs field to tunnel from this wrong minimum, if you will, to the electroweak minimum, and you would get this first order phase transition in the Higgs field in the very earliest moments of the universe. And so you can read about this in this paper that I wrote actually just last week. So I've given you the first ingredient. So I've given you a phase transition now at a very high temperature, right? Because remember that the instability is at 10 to the 11 GeV. So these are the kinds of things that need to happen at temperatures above 10 to the 11 GeV. So that's the first requirement. The second requirement, of course, was that the bubbles need to be ultra-relativistic, right? And that turns out also happens. And that happens because this phase transition here is now a special one. It's a symmetry restoring one, right? In other words, in the initial phase, when the Higgs is sitting in the deeper vacuum, all of the standard model particles are very massive because the Higgs has a very large VEV. When it transitions to the electroweak minimum, or essentially zero VEV, then all of the standard model particles will lose their mass and they become massless, which means that as the bubbles expands and interacts with the plasma that is trying to go from very heavy particles to very light particles, the dynamics is such that the bubbles will actually accelerate, even though the interactions with the plasma are very strong. And it turns out that the Higgs bubbles would reach pretty ultra-relativistic speeds despite these interactions in the standard model. And so you can read about this in this new paper that also just came out last week. And the bottom line is that in this modified inverse electroweak phase transition, if you will, it is possible to produce right-handed neutrinos that are heavier than the temperature of the plasma, and it is possible to do leptogenesis in the way that I told you about in the past few slides. So this is work in progress. Hopefully, will come out very soon. So let me just summarize my main ideas here, and thank you for listening.